So, students, we will be meeting today to discuss our next chapter, that is what is termed as the dynamics of rigid bodies. And here, mainly, we will be talking about the two-dimensional motion of the rigid body in terms of its kinematics and kinetics. And if you recall our last chapter that we had studied, that was actually, the dynamics of system of mass particles. And at the fag end of that chapter, we tried to define a rigid body mathematically. A rigid body, as we know, just recapitulate, is an infinite collection of many mass particles where the instead of masses to be discretized, the masses are continuously distributed within the domain of the body, which can be idealized as to be a collection of infinitely many mass particles, such that the distance between any two particles within the domain of the definition of rigid body, that is going to be constant irrespective of the magnitude of the forces and moments, external forces and moments, which may be acting on the body. So it means that if we take any two constituent mass particles within the domain of the body, we will find that the distance between these two mass particles is basically going to be unchanged, or it is going to be constant throughout the period of motion of that body. And this definition of constancy between the two mass particles is going to be absolutely true for the case whether the body is executing a plane motion or it is executing a three-dimensional motion. So if we just the study and as it is customary that when we will be going to study the rigid body dynamics, we will first begin with the geometry of motion, that means the rigid body kinematics. And if we just notice here, what we will find is that the rigid body motion is actually can be classified into the two groups, which are called the plane motion, or which is this is basically called as to be the two-dimensional motion, and the other one is termed as the space motion, which is three-dimensional motion. And both these two types of motions, that means the plane and the space, can be further classified depending upon the geometry of the motion that the rigid body is going to execute into the three such groups. The first type of the motion, which is basically called as the translational motion of the rigid body, and in case of this translational motion, it can be further classified into two groups or two types. One is termed as the rectilinear translational motion of rigid body, both in plane and space, and then it can be both in plane and space the translational motion, in which the rigid body will actually translate, instead of rectilinear path, it will translate in any curvilinear path. So curvilinear translational motion can be another example. Then we have the rotational motion of the rigid body, both in 2D and 3D, where the rotational motion can further be classified as about a rotation of the rigid body about an axis, or rotation of a rigid body about a point. Actually, in case of the three-dimensional motion of the rigid body, the full-fledged the meaning or the complicacy of the rotational motion of the rigid body can only be appreciated if someone actually undertakes the study of the space motion or the three-dimensional motion. Again, and lastly, the geometry, the motion can be, the combined form of this translational motion and the rotational motion. This is called the combined motion, or sometimes known as the plane motion. This is actually typical combination of this translational motion and the rotational motion. Now here actually we have mentioned the two types of motions as plane and space, but as we say that our first study will basically begin with the plane motion of the rigid body, and when we understand the dynamics of plane motion, then only we will be able to take up the space motion, which is of course and obvious that it is going to be more complicated than the plane motion. So our study in our present scope of work will be to discuss or confine ourselves to the discussions of the plane motion of the rigid body. And in doing so, we start with the plane kinematics, and we'll first take up the translational motion, which we recall that can be of two types. One is called the rectilinear translational motion, another one we may call it as to be the curvilinear translational motion. So as we know that in case of translational motion, every point of the body which moves in the congruent parallel curves for curvilinear translation, or it will moving along lines for the rectilinear translational motion. And we see that it is the simplest type of motion and geometry to study the kinematics. Say for example, here if we just try to illustrate or elaborate this type of motion, what is termed as this one, the translational motion, if we try to elaborate it, we just can say that in this case of the plane in case of the plane translational motion, suppose if we consider, say this is a rigid body, let us say this is a rigid body, and we see that after, say this was at the position at time t equal to t1, and let us take on this rigid body domain, let us take one mass point here and another mass point there, and after some time, say this is at time t equal to t1, let us consider this is the time at t equal to t1, and after some time, say at t equal to t2, let us suppose that the body moves into this position. Let's say it moves into the position over here. So this is the position of the body, suppose at time t equal to t2, at time t equal to t2. And if in this when it comes to this position, the actual the path by which this body will travel from this position to this position can be either a straight line, if it is a case of rectilinear translational motion, or it can be a curve. Say for example, let us consider the curved one, because the rectilinear translational motion is very easy to picturize. But suppose if we try to move in a sort of in a curved path, let's say this is the curved path in which the particle is taking to this position, and then we will have the congruent and parallel path by which you see that if we consider this particle as particle A at time t equal to t1, and this is the particle B at time t equal to t1, suppose that this particle A moves to the position A prime after time t equal to t2, and the particle B occupies the position B equal at the position B prime, what I will find that the individual path taken by the particle A or the particle B, these paths are congruent and they are parallel to each other. It can be a curved path like this. If it moves in a curved path in this manner, we say that the rigid body has undergone a curvilinear translational motion. On the other hand, if this path, the individual paths followed by the particle, moves along the straight line, here also it moves along a parallel and equal straight line, then we will find that we will rather say that the rigid body is undergoing rectilinear translational motion. Now, what is most important in this case, that if we take any other point here on the body, the same point also will move in the same manner. That means, what I mean to say is that the same curved path or the same line can be taken actually to predict in which way the point C will be moving to the point C prime. Suppose this is the position. That means if I take this AA prime, if I take the BB prime, let us suppose that this is the body is moving in a rectilinear translational motion, then we will simply just put this straight line, that magnitude and direction all remains the same. We'll just place this straight line here connecting the point C, and we will be able to find what will be its position at time t equal to t2. So therefore, you see that if we just follow the motion of a single particle in case of translational motion, either in a rectilinear or in a curvilinear way, we will see that we can define the motion of all other particles belonging to this rigid body. So therefore, it is sufficient to actually study the motion of a single particle when the motion is basically translational in nature, because we do not study the motion of multiple particles, because we will see that the motion of all other particles will be exactly congruent to the motion of the particle under investigation. So that is number one. That is it is sufficient to consider only the motion of a single particle. Another major important thing is this, that the orientation of the rigid body in case of the translational motion is going to be unaltered. What it means by saying is that, suppose if I join these 2 points A and B by means of this line, we will find that the same line, that means this distance, since it is a rigid body, the distance between this is going to be constant all through. So it means when it comes to this position at time t equal to t2, the distance between A and B is remaining the same. That is number one. And in case of translational motion, what is further important is that since this body does not change its orientation, it means that this line AB and this line A dash B dash, they are going to be parallel to each other. So first thing that we need to know is we need to understand that the distance between the 2 points AB is going to be equal to the distance between the 2 points A dash and B dash at time t equal to t1 and at time t equal to t2. That is number one. This is from the rigidity definition of the body. This we can say as the rigidity definition, that since the body is rigid, the distance between any 2 constituent particles is going to be constant. So that is number one. And number two, since it is a case of translational motion, we find that the orientation of the body, since it is unaltered, is see that orientation, since it is being unaltered, we note that AB is going to be parallel to A dash B dash. So in this part, and it is independent of the fact whether the rigid body is executing a curvilinear translational motion or it is executing a rectilinear translational motion. That means in case of the translational motion, we will find that the distance between these 2 lines, that means if we join these 2 particles, any arbitrary particles, defining the definition boundary of the rigid body, we will find them to be parallel to each other like this. So we see that this is an illustration of the motion of a translational motion of a rigid body. So going back to our discussion, you see that it is the simplest type of geometry to study its kinematics, and it is sufficient to follow the motion of a single point belonging to the body, as the motion of all other remaining points will be identical for all the particles in the body. Here, orientation of the body also remains the same, that we have already illustrated. So that is what is termed as the translational motion of a rigid body. Now next comes is the rotational motion. Actually this rotational motion in case of the rigid body dynamics actually provides the most variety, and this rotational motion characteristics differentiates the complexity. It differentiates the complexity of the motion of the rigid body. And the effect of this rotational motion in case of the rigid body motion will be more prominent, as we have already mentioned, if someone undertakes the space motion or the three-dimensional motion of a rigid body. So in case of rotational motion, we see that every point except the center of rotation will move in concentric circles whose center is the point of rotation. So if we just see in case of the rotational motion, so what we see that, suppose if we go to the illustration once again, we will find that say for example, if we consider that same old rigid body here, say let us consider this is the rigid body, and let us suppose that this point, suppose this is the point A, it is considered to be the center of rotation of this body. So what it means is that only this point is going to be, and it is, it is only undergoing pure rotation. So the rigid body is rotating with respect to point A, and it's undergoing pure rotational motion with respect to point A. That defines that out of all the points, only this point A, which is considered to be the center of rotation, is the only point which is inertially fixed. That means if we consider again, say this is the position at time t equal to t1, and let us suppose that after time t equal to t2, we have this body once again. So this is the body. Let us place it here like this, and then we slowly begin to rotate the body in this manner. So what we do, we just take the this rotation may not be able to, we will not be able to display this with this diagram. So let me just take this way. So this is the body, suppose, and after time t equal to t1, say the rigid body goes to this particular domain. So this is at the position at t equal to t1, this is t equal to t1, and this is the position at t equal to t2. So at t equal to t2, what I will find is that this point B, actually if we join these 2 points here, considering this point as the center, what I will find is that this the point B, which is considered to be here, it moves along a circular path. So this moves along a circular path. Let us suppose that this is the position where it goes to the new position, let's call B prime. So what we find is that the point B moves to the point B prime, and here again if we try to join these 2 points A and B prime, what I will find that this AB prime, that means the distance between this AB and the distance between the AB prime, they are going to be same, right? And this will again come from that rigidity concept. Now let us suppose that we have another point here. Say this is the point C on the body, and what I will find is that due to this rotation, so again let me join this A and C, say this is the point C, and let me join this A and C, and we just measure how much is the angle of rotation. The angle of rotation is defined by this angle, the angle made by the successive positions of the 2 points on the body. Say in this case, the point A is here the center of rotation, and here we have, this is the point B, another point B, and we say how we track the point B to the position B prime at time t equal to t2 when this rigid body is rotating, is undergoing pure rotation with respect to point A. So I will now take the successive positions of these 2 points, and I will say here that if we just join this angle, define this angle, we say that the angle BAB prime, we call this angle as theta, and we say that this is actually the the amount of rotation. So we can say this, we can say as the angle of rotation. We can measure it in degree, we can measure it in radian, whatever unit we may feel like, but this will be the angle, and this is going to be the same for every other point on the body. So what I mean to say is that suppose if we bring in another particle C here, join this point A and C, again you see this is going to be constant, and now you simply have to rotate in order to locate the new position of the point C in the motion. What you need to do, you simply need to rotate this line AC, with center as A, and you need to rotate it along a circle. So you see basically this will this rotation will actually follow it will follow actually the concentric circles of different radius whose center is the center of rotation. So we just draw the circular arc. So we just try to draw the circular arc here. So what we do, I just show it here like this. Say this is our point C, and we try to join and show this circular arc. So we follow this circular arc here like that. So suppose it comes to this location C prime. So this comes to the location C prime. And if we join now this A and C prime, the angle between these 2 successive positions, that means the angle between AC and AC dash. So you see this angle will also be equal to theta. So this is actually going to be the characteristic of rotation. So we can say here the angle between CA and C dash A, so angle CAC dash is also going to be equal to theta, and it is going to be true for all other points on the body. So we say that this angle will define our actual amount of rotation, and we can express it in either degree or in radian. So what we therefore see from here, we note that every point except the center of rotation will move in concentric circles whose center is the point of rotation. In this type of motion, you see here the orientation of the body changes, as we note that the line segment AB and the line segment AB dash, this is AB dash, and the line segment AB dash, they are differently oriented in plane. So we note therefore that the orientation of the body is going to be changed, is not going to be preserved here, unlike in case of translational motion. So in case of rotational motion, we find that the orientation of the body changes, and the angle made by the line joining any 2 points on the body with respect to a fixed direction defines the orientation of the body at a particular point of time. So by saying that, what we mean, suppose if this is a rigid body, and let us suppose we take 2 points on the body AB. Through the point A, if we consider a fixed direction, that means suppose this horizontal line is drawn and it is taken to be our reference. So if we consider this to be a fixed direction, we can actually, join these two line segment, two points by this line segment, and consider this angle as theta, and we can say that this angle theta will define the orientation of this body at a particular point of time. Why it is so? Because after time t equal to t1, suppose this body is rotating, say with respect to point A. We just now show how that such kind of rotation can be depicted in the figure. So it is being rotated. So if we suppose that, say in this case, if we suppose that this is our, the fixed line, suppose this is our fixed line, we can suppose, and you see that the initial orientation of this line, we can define it by this angle. The initial orientation of the entire rigid body can be defined by this angle, which is being which this line segment AB is making with this fixed direction. So this direction is not going to change at any point of time during the course of motion. And if we take this angle, let us call this angle as phi, then this phi will define the initial orientation of the body. And if theta is the amount of rotation of that same line segment after time t equal to t2, then we can say that phi here, we can define it to be the initial orientation or orientation of the body, initial orientation or the orientation of the body at time t equal to t1. We can define it like that, orientation at t equal to t1. And if we suppose that theta is the amount of rotation, then at time t equal to t2, at t equal to t2, the new orientation will become the new orientation of the body. New orientation of the body will be equal to how much? Will be the angle made by the same line with that same fixed direction. So this is the fixed direction, will be obviously how much? Now that will be equal to the initial orientation plus the angle of rotation if the two angles are in the same direction. If it is such that the rotation is taking in opposite sense, in this case here you see the sense of the initial orientation is in the anti-clockwise direction when you are looking from the front of the figure by judging this arrow, correct? So if the rotation of the body occurs in the opposite sense, that means at time t equal to t2, the body rotates in the clockwise direction, then obviously the new orientation of the body will be equal to phi minus theta. So in this case, we assume that both the rotations are in the, both the senses are in the same way. That means the initial orientation is measured in the clockwise, anti-clockwise sense, and the actual rotation that the body is undergoing is also, defined by the anti-clockwise sense. So in case of rotation, we see two things are important. Firstly, the amount of rotation. So three things are going to be important. First one will be what is the center of rotation. Center of rotation. You need to define the center of rotation. That is the first thing. The second thing is the amount of rotation. We can say the amount of rotation that we need to see. And next is the sense of rotation. That should be the sense of rotation. And when we say sense, you see that in case of the plane rotational geometry, this sense can be clockwise or it can be counterclockwise or anti-clockwise. So we need to actually, define all these three things before we are going to study the rotational motion, plane rotational motion of a body, of a rigid body. And all these motions are pure. I mean to say there is no other component other than the rotation of the body. So here if we see that if we consider another two particles, say C and D, here angle theta is actually defining our rotation, our orientation. So if we consider another two particles C and D, consider that same fixed line, and if we suppose that the angle between this line segment AB and CD is beta, again you can see from the definition of the rigidity of the body, the angle between these two different segments is going to be unaltered. Because it is a rigid body, this angle between the two different points on the body, they are going to be unchanged. So if we consider this angle as beta, so that is going to be constant. So as far as the line segment AB is concerned, this orientation can be considered as function of time. So we can write it as theta of t. And if we consider this angle beta, which is of course going to be constant, and as far as this line segment CD is concerned, the angle made by this CD with the fixed direction obviously will be going to be theta plus theta of t plus beta. But since you see that this beta is going to be constant, we find that if we try to differentiate this with respect to time, you see this will give us the angular velocity. That means if we differentiate theta with respect to time, that will be giving us the angular velocity omega, because the orientation of the body with respect to this fixed direction can change depending upon the case whether the body is actually changing its orientation with respect to this fixed direction. And in case of rotational motion, say in about the point A, suppose in case of the rotational motion of the rigid body, this orientation is definitely going to change. So therefore we can have the differentiation of this angle, and we can take this derivative of this angle, and we can take this as to be the measure of what is called as the angular velocity, what is termed as the angular velocity of the body. And we note that if we take some other line segment instead of AB, by say for example in this case CD, the new orientation is being defined like that. And even if I differentiate, suppose we can call this angle as psi. So if we now differentiate, because this is function of time, this psi is also going to be function of time. So if we differentiate this with respect to time, what I will get is that psi dot will become equal to theta dot. So it again gives me the angular velocity omega. So it does not depend upon the fact that which angle I am going to take. And obviously if we differentiate this theta dot once again with respect to time, we will be getting the theta double dot, which will give us omega dot, which is the angular acceleration of this body, which is undergoing plane rotational motion. So the body is undergoing plane rotational motion. The rotation is taking place about the point A. Actually, we have here the center of rotation, as we have mentioned here, that this is the first thing that we need to define. And with this center of rotation comes the concept of what is termed as the axis of rotation. What is basically the axis of rotation? The axis of rotation here will be an imaginary straight line that is going to be passing through point A and going to be perpendicular to the plane of this body. So if we imagine a line, a hypothetical line, which is coming out from the plane of the screen or going into the plane of the screen through the point A, then that particular line will be considered as the axis of rotation. In case of plane rotational motion, this axis is, this type of rotation is actually termed as the fixed axis rotation. we call this rotational motion as the fixed axis rotation, in the sense that during the course of this rotational motion, this axis, which is always passing through the point A and always remaining perpendicular to the plane of this body, is not going to change its own orientation. So if it say points towards vertical, then it remains towards vertical throughout this rotational motion. So it is always is considered to be a fixed direction. It is, this line is always along the fixed direction, or it is absolutely fixed. So that's why this plane rotation is termed as the fixed axis rotation. But as you will undertake the three-dimensional rotational motion, you will have to deal with the complicated cases where this axis of rotation can also change its own orientation. That means the axis of rotation can also follow some angular motion, which is giving its oblique motion of the body, and that will actually define the three-dimensional rotation of the rigid body. However, as we have reiterated also, that right now we are not going to discuss the three-dimensional rotation of the body, and we will be therefore confining ourselves to the discussion of the plane rotational motion. So having defined therefore the first two types, I mean to say the translational motion and the rotational motion, now it's the time to introduce the case of the combined motion, or which in this case is termed as the plane motion. Simplistically put, it is a combined motion having both the pure translation and the rotational motion. We can understand it by by considering, say this is a rigid body, as we have already seen, and at time t equal to t1, and after some different time at t equal to t2, let us suppose that this is our new geometry of the body. So if we carefully look, we will find that the orientation of the body changes, and at the same time there is some translational component. That means if we suppose, let's take 2 points belonging to this body A and B, and when the body they are at time t equal to t1, but when the body occupies this new geometry at time t equal to t2, let us suppose that the point A moves to the location A prime and the point B goes to the position B prime. So once again, if I join these two line segments AB and A dash B dash, what we will note from the definition of rigidity, this AB line segment and this A dash B dash line segment, they are going to be equal, because that will come from the basic rigidity definition of the body. Second thing that we note here is that AB is not parallel to A dash B dash, indicating the fact that there is some change in orientation of the body. And we have just now seen that the orientation of a rigid body during the course of motion can only be achieved if it undergoes rotation about some point or about some line. So let us try to see how here the both these components of translation and rotation can be involved. For that, let us suppose that we take the point A as our reference point. So what we do, we first bring the body at the geometry from at time t equal to t1 to this new position, such that the point A gets coincided with A dash. That means the changed location of the body in the changed geometry. So this is therefore the final position of the point A during the course of motion. Please note, A is the initial position of a point on the body, A prime is its final position. Similarly, B is another initial position, initial point on the body, and after motion the point goes to the location B prime. So if we first consider the case that we bring this body in such a manner that the point A comes to the location A dash. And during this course, you see that we give this body to a translational motion, and that translational motion can again be rectilinear or curvilinear in nature. In this case, we have illustrated this motion as to be the rectilinear translational motion for simplicity. So what we do therefore, we bring the point A to its final position, and while I am doing this translational motion, the point B will move in the parallel path and will take the position B double dash, where A dash B double dash is equal to AB. And first thing, and second thing is that we need to write that AA dash is going to be parallel to BB double dash. It is going to be parallel to BB double dash. So the line segment AB and the line segment A dash B double dash are parallel. So obviously B double dash is not the desired image or the desired location or the final location of the point B on the body. What is the final location of the point B? It is to this B prime. And what is the final location of the point A? It is the point A dash. So we note that the point A has reached its final location because we have chosen it to be so. However, the point B does not achieve its final location. So it has come to say some sort of intermediate position. So in order to bring this point B double dash, that means the intermediate position of the point B to its final location, that means the point B dash, what I need to do is just give this body a rotation with respect to the point A dash. So what we will say? We will give some amount of rotation. Let us say this amount of rotation is theta. So we see that we therefore, give the rotation to this body with respect to the point A dash such that B double dash comes to its desired final location B dash. And thereby, if we join this A dash B dash and A dash B double dash, we will see that this theta will define the required amount of the rotation that needs to be provided to this entire description so that we can map the final orientation and the final position of the rigid body with respect to the initial position and initial orientation of that same body. So we see that this type of, the arbitrary plane motion can be thought of as a combination of a translational motion and a rotational motion. This in fact is the underlying statement of what is called as the Chesel's theorem. Now, there is another very interesting thing. Suppose in this case we have chosen, say for example in this case we have chosen the point A in such a manner that we have brought this initial position of the body to the final orientation in such a manner that the point A has been taken to its final location. But what would happen if we go in the reverse way? That means we will bring the body in such a manner that first B will be taken to its final position. So what we will do? First, we will now give the translation to this body, again assumed to be a rectilinear one for simplicity. So give the translational motion to this rigid body such that the point B, the mass point B on the body actually comes to its desired final position. So it comes to the location B prime. Naturally, you see, when I will have this translational motion, that means the amount of translation here is BB dash. Earlier, the amount of translation was AA dash. Clearly, these two translational motions are not equal. Correct? Because the amount of translational motion varies. Although they take place in the same direction, but or rather same sense, but their amount is actually different. So we have brought the point B to its final location B dash, and during this course of motion the point A has come to this location A double dash, which is considered to be its intermediate location. Like we had the point B double dash as the intermediate position of the point B when we made the point A to come to its desired final position. So in this case, the point A has now reached an intermediate location. So, but it is not its final position. Final position is of course A dash. So how to, and we have already gone, we have already, taken the point B to its final position. So no more further translational motion is possible, because then B dash will also change its position, which is not actually allowed, because this is the desired final position of the point B. So what I will be having, I'm left with only one alternative. What is that? Keep B dash fixed in its final position and move the body such that this intermediate position A double dash comes to its desired location, that means at A dash. And this is possible only when we rotate this body. You see here now the same, here this rotation, we have shown these two rotations, earlier rotation also and now the new rotation also, by these two different things, and we see that the senses of rotation are the same. That means both are in the anti-clockwise sense in this case. So the senses of rotation remains the same. Whether the amount of rotation will remain the same or not, that we will come to explain now. So we see that this line segment B dash A double dash, it will now come to the location, this location A dash. Now you just note from here, earlier we noted that this line segment A dash B double dash was parallel to, the line segment, what is called the line segment AB. So this we say that AA dash, sorry, here it will be AB. I'm sorry, I made a mistake here. So actually, the line segment, it was actually defining AA dash. Oh, okay, it was okay. Acha. So what we try to say is that now, right, is that what we say, that since it was a translational motion, earlier case, you see that AB, the line segment AB was actually parallel to the line segment A dash B double dash in case of the first situation when we brought the point A to its final position. And now when we go for the second method, that means when we bring the point B to its final position, we see that the line segment B dash A double dash, the line segment B dash A double dash is this intermediate location of the point A. So we note that B dash A double dash is also parallel to, the line segment AB. So it means that B dash A double dash is actually parallel to A dash B double dash. And also, you see B dash B double dash is parallel to A double dash A dash, because both are actually giving you the translational motion. So it therefore shows that this quadrilateral A dash B double dash B dash and A double dash, the quadrilateral that it has formed here is basically a parallelogram, and whose diagonal is A dash B dash. So obviously then these two angles, they must be equal. So therefore we conclude from simple geometry, Euclidean geometry from here is that although the translational component of the motion may vary, because it depends upon how you are bringing your point to its final location. That means whether you are bringing the point A to its final location or whether you are bringing the point B to its final location. So it varies. So although the translational part of the motion, it can change, it can vary in magnitude, the sense and the directions remaining the same, the rotation, the amount of the rotation and the sense of rotation, they remain unaltered, although the center of rotation can change. For example, in the earlier case, the center of rotation is obviously the point A dash, which is the final position of the point A. And in the second case, when we illustrated this motion, we note that the center of rotation is this time is, you see, B dash, which is the final position of the point B. So you can change your center of rotation, but actually the sense of rotation and the amount of rotation, they remain unaltered in case of this plane motion. So this is a very important, the observation as far as the plane motion of a body is concerned. So therefore, by virtue of Chesel's theorem, we can always say that a plane motion, we can always think it of as a combination of a translational motion and the rotational motion. And how that combination can be thought of, we can illustrate this with this example. And we showed how even if we change our, the point of reference, we will be arriving at the same amount of rotation and its sense of rotation also remains the same. So having discussed therefore the three types of plane motion of a rigid body, meaning say the translational motion, pure translational motion, so to say, then pure rotational motion, and then the combination of these two as the plane motion, we are now going to study the kinematical analysis of this rigid body. So just now, so far, what we have discussed is the geometry of the rigid body motion. Plane motion of a rigid body can be either a translational motion, whether it can be a rectilinear translation or it can be a curvilinear translation. Then we see that it can be a pure rotational motion, and then we see that it can be a combination of translational and rotational motion. Now, once we have discussed the geometry of the motion, let us now try to understand what are the methodologies of analyzing such motion, which is basically known as the kinematical analysis of the rigid body motion, which is of course the plane motion. And in this case, we can classify the analysis methods for finding out the velocity as well as for finding out the acceleration. So we can, that we can go for the velocity and we can go for the acceleration of this thing. So this is applicable for both the velocity analysis as well as for the acceleration analysis. And we see that the analysis methods can be many types. Firstly, it can be the absolute motion analysis method, by which we can analyze for the velocity and acceleration of a body. Then we can apply the concept of relative velocity and relative acceleration to study the kinematics. Then we can have the vector analysis method to study the kinematics, and we can have the concept of instantaneous center of velocity method. However, this particular method is only applicable for the velocity analysis, although in the analysis methods we will take care of both the velocity and acceleration of the rigid body. So in this case, therefore, except this instantaneous center of velocity method, all the other methods can simultaneously completely analyze for the velocity and acceleration of a rigid body. However, this instantaneous center of velocity method will only be applicable for finding out the velocity of a point on the body. So we will try to now illustrate every method one by one, but we will exactly not follow the order in which I have mentioned here the different methods. So the order I can vary, and of course we will start with this absolute motion method. That will be our first methodology. However, the remaining methods we may not follow the order in which the methods have been here listed. So we begin with now the absolute motion analysis method. So in this method, basically what we will be going to do is that the geometry of the instantaneous configuration of the rigid body or a system of rigid bodies. Here, you know that we may have a single rigid body or we may have interconnected rigid bodies, which we call as to be the assembly of rigid bodies. And this is very important because this assembly of rigid bodies often lead to the concept of mechanisms. Mechanisms are nothing but assemblies of several rigid bodies where the motion is modified, that means, and transmitted from one point to another without any transmission of the force. So you can have, in case of mechanism, we will simply consider the modification or the transmission of motion from one point to the other point of the system. Correct? That assembly of several rigid bodies can actually, can be assembled to perform this kind of the transmission or the modification of motion. By modification of motion, what we mean that sometimes that a machine must be there where the rotational motion needs to be converted to a rectilinear motion or vice versa. So this is called as the modification of motion. And it can be the motion transmission. That means motion is being input at one end of the system and I need to transmit this input motion to some other location in the system, and then it will be called as the output motion. And in this case, we will say that the motion is being transmitted from one end of the system to the another end of that same system. So the system of rigid bodies, there can be a single rigid body, there can be a system of interconnected rigid bodies performing this type of duty, and we will call that entire system as a mechanism. So in this case, the geometry of that instantaneous configuration of the body, it may be a single body or it could be the mechanism, is analyzed, and then differentiating the appropriate parameters, we get to obtain the instantaneous values of velocity and acceleration. So you see, by stating this, we may not understand the full meaning of it. So it is better that at this point, further elaborating the concept in words and sentences, let us take a concrete example to illustrate the basic inherent concept of this absolute motion analysis. In doing this, let us take an example from the book of Merriam and Craig, and we will going to take few examples here to illustrate the basic concept of absolute motion method. And in doing so, we will be taking several examples from the book and we will try to follow, explain the different steps that have been, used here. For example, let us take this problem from the book of Merriam and Craig, the problem number 5/34. In this case, this is the associated figure that we have shown here. We note that what is the figure actually telling us? You see here, there are two slots. The two slots are there. Of course, they are in the same plane, in the same plane. So one slot is so-called horizontal slot and another one is an inclined slot. It can be a horizontal plane. I mean to say, these entire slots can be in the horizontal plane or it can be in the vertical plane. Anyway, that doesn't matter right now for us because we are not interested how the motion is caused. We are interested only that once the motion begins, what will be the situation. So let us consider that these are the two slots in which we have some, the two slots, or you can say the two guides, within which two blocks defined by block A and block B are destined to move. That means this block A is moving in this slot or in this guide, while the slot B is going to move along this inclined slot or in the inclined guide, and these two slots motions are synchronized by connecting them by means of this rod. So here actually this rod AB, which is of length L, is going to consider as to be this, we are considering as to be our rigid body. So what we say is that for this type of this thing, so as you see, it is very pretty obvious, as this actually this block will be moving along this guide with some velocity. Since it is connected by means of this rod, the motion from here, let us, if we call this as to be the input motion for understanding, then the motion from here, from this point, will be transmitted via this body to the point B. So you see that if we therefore give some motion to this slot, to this block A, that motion will get transmitted to this motion, to the motion of this block B. And therefore, why it is being done? Because they are connected by means of this rod. And while they will be moving, this rod will execute some plane motion. So there will be some translational component as well as the rotational component. But in this case, what we try to see is that slider A moves in the horizontal slot with a constant speed V, as shown here by this green arrow, that it is moving with a constant speed. So this V is going to be constant for a short interval of motion. Determine the angular velocity of this bar AB in terms of the displacement XA, where XA is the distance of the instantaneous location of this slider from this point of intersection of these two guides. One thing we need to remember before we proceed further, this is a very important thing that we should understand, that whatever velocity or acceleration analysis that we will be going to do in this class, they are actually are all instantaneous in nature. That means at a particular instant of time, given this geometry or given this configuration of the mechanism or the rigid body, what will be the instantaneous value of the velocity, angular velocity, instantaneous acceleration, angular acceleration, etc. The moment the geometry changes, these things will of course change. However, in some cases we may connect them by means of some mathematical equation so that we can actually predict as time passes if the geometry changes from one configuration to another configuration, how the velocity and other parameters are going to change. For example, in this case, we need to calculate the angular velocity of this rod in terms of this position, current position of the slider XA and the given length L, because this is is the system parameter, and the angle between the two guides has been mentioned to be equal to 60 degree. So in order to analyze this by means of the absolute motion method, what we need to do, first thing that we need to define the geometry, given geometry, and we need to write some mathematical equation by means I can actually represent this given geometry. So how we can do it? There can be several methods. How we can do it? The best way of doing is that, let us suppose that we erect some reference frame, inertially fixed reference frame, keep my origin at point O, which is the point of intersection of these two guides, which is absolutely fixed, of course. So this is point O, and the associated axes are all inertial axes. Now, if we join the current locations here, we will find that we create a triangle of which I can have this angle 60 degree, I have this length XA defined, as also I know that distance between these 2 points, which is equal to L. Since we need to find out the angular velocity of this rod, I need to therefore define certain orientation parameter of this body, because in order to find out the angular velocity and the angular acceleration of a rigid body, in this case the rod AB, we need to define some orientation angle with respect to some fixed line. So in this case, the fixed line is of course this horizontal slot, or rather the x-axis. So what we do, we define this angle theta in this way. Someone can define this angle as well, but let us say that we define this angle theta. The sense of course is going to be from here to this way. So this is how we define this angle theta here. Always you need to define the angle by giving this arrow. By that it will actually provide you the sense of the angle, and if there is any change of that angle with respect to time, in which sense that angle is actually going to vary. For example, in this case we have shown the arrow such that we measure that all our clockwise rotation when looking from the front to this figure are taken as to be positive. If someone wishes to define the orientation of this angle of this rigid body AB by means of this angle, of course, then you need to define, say, this angle in this manner, and then you need to put the arrow in this way, and all the cases here, then you see the anti-clockwise motions or senses are going to be considered as positive. So that is an alternative thing you can try with that particular concept at your home. So you see, therefore we define, so we therefore come back to our geometry story. We say that we therefore see a triangle here for which I know this length side, I know this side, and the two angles now are defined. So therefore it is prudent for us actually to apply the sine rule to this triangle, and thereby we try to define the instantaneous geometry that is being created. So you see, therefore applying the sine rule to the triangle OAB, I can write this L by sine 60 degree is going to be equal to XA divided by sine 60 degree plus theta, because we need to find out this angle. And of course, if these two angles are defined, we can find out this angle as 180 degree minus 60 degree plus theta. So sine of 180 degree minus 60 degree plus theta is just sine 60 degree plus theta. So we can say that it is L by sine 60 degree is going to be equal to XA by sine 60 degree plus theta, from where I can find out this XA, and that we can write it as sine of 60 degree plus theta divided by sine 60 degree into L, and we call this as equation 1. Now see, once I define this, considering the motion, you see theta is a function of time and XA is also a function of time, because the block A is moving, and the velocity of the block A being given here will evidently is nothing but the time derivative of this dimension XA, correct? So if we differentiate this equation with respect to time, keeping in mind that XA is a function of time as also theta, and all other parameters are constant, we will be able to connect the velocity with the remaining things. So therefore, proceeding in that way, if you simply differentiate, we get dxa dt, which will be L by sine 60 degree, because this is going to be constant. Then we can write it to be cos theta plus 60 degree, and of course it will be d theta dt. So because your theta is actually time varying angle, so we can say this d theta dt, as per our the concept here, this d theta dt will be theta dot, and this is going to be our angular velocity of this rod OB. So we can say that it is d theta dt is nothing but theta dot, which is L omega, and L sine 6 is there, so it will be L omega AB, and then it will be cos theta plus 60 degree by sine 60 degree. So how to, but we know that dxa dt is plus v, this is being given for us, so we can further simplify it algebraically. Since our objective is to find out this angular velocity of this rod, we write this in this manner that omega AB will be equal to V by L into sine 60 degree by cos theta plus 60 degree. Sine 60 degree is root 3 by 2. So we simply write root 3 by 2 into V by L into 1 by cos 60 degree plus theta. Now, you see, we come to this geometry because our objective is to express this angular velocity in terms of XA. So we are half done to it because in this case we have already introduced this geometric parameter theta, but we are to eliminate this geometric parameter because we need to express all our answers in terms of XA. So therefore it will be our objective to eliminate this geometric angle theta. So how we can do it? We take this equation once again, that XA is equal to sine of 60 degree plus theta divided by sine 60 degree whole into L. So from this equation, we can say that sine 60 degree plus theta is equal to root 3 by 12 into XA. And our objective is to find out cos 60 degree plus theta. So evidently we can say that cos 60 degree plus theta can be expressed as like this, which is simply root over 1 minus sine square 60 degree plus theta. So it is very simple to find that it will be 1 by 2l into root over 4l square minus 3x square. And now when we know this cos 60 degree plus theta is known, see, now we can come and put it into this equation. So from 1 we can therefore say that, so now from here, so you see this is where we left. So we come back to this by substituting this expression over there and can continue that omega AB will be equal to root 3 by 2 into V by L into 2L by root over 4L square minus 3x square. Again, if you arrange it like that, we see omega AB and all these are coming with a plus sign. So what it means is that that we initially considered that all angles will be measured in the clockwise direction. I said that you can of course defy me and can define alternatively by defining this angle in the anti-clockwise sense to proceed your picture. So it is very important in which way you are defining your initial orientation. In this case, the initial sense are taken in such a way that all clockwise motions are taken to be positive. And throughout this calculation, we never encounter with any negative sign. So it means therefore that whatever sense we have assumed at the start of our solution is going to be correct. So we can peacefully say that omega AB is equal to, the LL getting cancelled can be written as root over 3V by root over 4L square minus 3x square. And of course, this angular velocity is in the clockwise sense. You need to remember one thing. When you are being asked to find out the velocity, angular velocity is a vector quantity, correct? Angular acceleration is a vector quantity, because you know from your school days physics that all finite angles are not vectors, although they possess the magnitude, they possess the sense, they possess the direction, all the three requirements of a vector quantity they possess, but they do not follow the parallelogram law of addition of vectors. That means A plus B is never equal to B plus A so far as the finite angle of rotation is concerned. However, it can be mathematically proved that if we bring down that finite angles to a smaller values, then at the limit, in the limit, infinitesimally small angles, they actually tend to follow the parallelogram law of addition of vectors or commutative law of addition of vectors. And therefore, all infinitesimally small angles are considered vectors, and naturally they are delta t divided by delta t will be a scalar quantity, delta t being a scalar quantity. So delta theta by delta t, of course, limit delta t tends to 0, we will get what is known as the angular velocity, which will be of course a vector quantity. And in that same logic, we can say the angular acceleration is also a vector quantity. Why I say is this, that whenever you are being asked to find out some velocity, be it linear, be it angular, or some acceleration, be it linear, be it angular, not only you need to mention your magnitude, also you need to mention about their senses. So here this arrow will give us the idea that this angular velocity is in the clockwise direction. So therefore we find that it is the required expression of the angular velocity of the rod. If required, the above expression can be further differentiated. So here it was not asked, but supposing the question is that you not only need to find out the angular velocity of that rod AB, you need to find out its angular acceleration. So what you need to do, you need to differentiate now this expression, keeping in mind that here it has been mentioned that your velocity is constant. What it means is that there will be no further differentiation of the numerator, but in the denominator the term is there where this xa is a function of time. So keeping that thing in mind, we can differentiate this expression further with respect to time to calculate the angular acceleration of the rod. And I will ask you to do it at your home. What will be the angular acceleration of the rod? Now, once this is found, see, it is noted that we have been able to calculate the angular velocity of the rod as a function of the instantaneous position, xa, correct? So it may so happen that someone can ask you what will be the angular velocity of this rod AB when xa is 0. That means when your slider is here, but you are moving with your velocity v, constant velocity, at that position, what would have been the angular velocity of this rod AB? So it is now very simple for you, because you know this is your general expression for the angular velocity as a function of the distance xa. Just put xa equal to 0 and you will be able to get that angular velocity, instantaneous angular velocity at the location xa equal to 0 of the rod will be nothing but √3/2 into v by L. So that will give us the instantaneous angular velocity of the rod when xa was 0. And in the same way, one can find out what would be the instantaneous angular acceleration of that rod at any position, so to say. So I hope that this example clarifies the basic concept of the absolute motion analysis method. So coming back once again, if we just summarize what we have done in the absolute motion analysis in this example, we first take the problem system we define, and then we try to apply some sort of concepts of geometry to define the current geometrical configuration. And once that current geometrical configuration is being defined, we identify what are the parameters which are actually functions of time, so that the motion of the system can be animated. So in this case, we note that xa changes, so xa is a function of time, and of course this parameter theta, that is also going to change subsequently. So in this example, the xa and theta, they are basically considered as to be the functions of time, correct? So once we identify them, then it is a straightforward process of differentiation. You need to differentiate once for finding out the velocities, and for finding out acceleration we need to differentiate once again. And you, in the process, you may need to do some little bit of algebraic simplification, the way we have done it here. I hope that with this example you have understood the basic concept of absolute motion analysis. So let us further reinforce our concept by taking another example. So this is a little bit, a complicated one. The earlier problem that we showed was consisting of a single rigid body. Now you see here we have a collection or a system of rigid bodies. So let's take this problem. So what this problem says, the piston rod of the hydraulic cylinder, so this is the piston rod and this is the hydraulic cylinder, of the hydraulic cylinder gives point B. Point B is what? This is a lever. ABC is a lever considered as to be a rigid body. So this is the point B, which is, the lever is of equal length. So this is the point B is the midpoint of the lever ABC. You can call this a lever, or you can call it in engineering sense, this will be called as a rocker arm. So this can be considered as a rocker arm as well. So at point B, which is the middle point of this rocker arm, here actually the piston rod of this hydraulic cylinder is being attached here. So you see this piston rod can be moved either in this direction, it can be pushed, or it can be pulled along. That means either it can extend its length or it can shorten its length. Thereby it will give some the motion to this member. And since this is being connected to another member OA, which is fixed here and connected here like this, so this point is going to be absolutely fixed and it is connected like this, and we call such members as cranks. So you need to remember these terms. So OA, this is basically called as a crank. This is called a crank. We term this as a crank. So it is a mechanism, therefore, because we have system of rigid bodies. So you see here, as you will be having something, there will be some sort of motions. And what it is being said, the piston rod of the hydraulic cylinder gives point B a velocity as shown. You see, this is being pushed. So the length of the rod is increasing in this direction. So this is VB. Determine the magnitude of the velocity of the point C of the rocker arm here. So we need to find out the magnitude of the velocity of the point C in terms of the angle theta, which is the angle between these two, this crank OA and the rocker arm ABC. So the angle between these two arms is taken to be equal to theta, and in terms of this theta, we need to calculate what should be the velocity of this point C. And the entire process needs to be done by the absolute motion analysis method. So again, for doing it, we take some axis, x-axis, y-axis, keeping our origin at this absolutely fixed point. Let us now first try to specify the location of the point B by this parameter called xb, and of course the location of point C, because this is the ultimate point for which we need to analyze. So we have this dimension we call xc relative to B. That means from point B, the position of C is being connected by this. So it is relative to the point B. This xc relative to B defines the location of point C with respect to point B, and also you see this will be yc, because this line is fixed. So this is not defined with respect to any moving point. Since the location of C is defined with respect to the moving point B, we introduce this notation of the relative position, and this is the fixed absolute position yc, because this line, central line, is absolutely fixed. That means this x-axis is absolutely fixed. Now since this is an isosceles triangle, so obviously this angle theta can further be written as this angle as pi by 2 minus theta by 2. This will be pi by 2 minus theta by 2, and we notice that here the angles are is moving in the anti-clockwise sense as far as this arm is concerned. So far as this crank is concerned, you see the angle orientation sense is in the clockwise direction. So for the crank, the clockwise rotations are taken as positive, as far as this rocker arm is concerned, you see the counterclockwise rotation is taken as positive. If we are accounted with a negative sign, we need to actually rectify our sense at the last. So once these things are defined, now again you note that we can apply the sine rule to this isosceles triangle OAB and can write this equation as xb is equal to 2b sine theta by 2. I think this is not to be explained, it is very simple for you, and this is the required geometry. So xb, that means this distance in terms of this angle theta, is being given by this xb is equal to 2b into sine theta by 2. Now if you differentiate, now you notice that xb's sense is along the rightward direction, while the point B is really having the velocity towards left. So Vb can be therefore written as minus x dot b, or x dot b can be written as minus Vb. So therefore, if we differentiate this equation with respect to time, keeping in mind that xb can change with respect to time as also theta, and also keeping in mind that dxb dt will actually define the velocity of the point B, and given the sense actually here in this problem dxb dt is equal to minus Vb. This minus sign significance needs to be understood very clearly. So we can say dxb dt equal to minus Vb, and differentiation continues like that. And you need to remember that we can say on differentiation, we can say that it is b theta dot into cos theta by 2. So we can say that this link ABC, omega ABC, if I want to find out this angular velocity of this entire link, we need to know that the angular velocity of this link is going to be differentiation of this entire angle pi by 2 minus theta by 2, correct? So if we differentiate, we see that it becomes omega AC. That means it will be written as, that means if we take this angle pi by 2 minus theta by 2, then obviously omega AC can be written as, we see from here, from this simple geometry, it is pretty clear that omega AC is nothing but, omega AC is nothing but ddt of pi by 2 minus theta by 2. So that is going to be my omega AC, which will be of course equal to minus theta dot by 2. So that is going to be my omega AC. So minus theta dot by 2, keeping in mind that theta dot is being given by this expression, so the minus sign will get absorbed, and ultimately we can say that b theta dot cos theta by 2, from this equation we can write it to be equal to minus Vb. So here, if someone also interested to find out what will be the angular velocity of this link ABC, we will have to use this equation to define our terms. So we see therefore that b theta dot cos theta by 2 is equal to minus Vb from this equation. So we define this as equation 1. Now we note that in order to find out xc, because we try to get the velocity of the point C, so we need to actually find out its absolute coordinate. So absolute coordinate means absolute distance from this point O in the horizontal direction as well as in the vertical direction. So what we do from here, that xc, which is the absolute location of the point C, is xb plus xc relative to b. So if we see that xb is already known to be equal to 2b sine theta by 2 from here, and how much will be xc relative to b? Since this is pi by 2 minus theta by 2 and this is also pi by 2 minus theta by 2, I can say that it is going to be plus b cos pi by 2 minus theta by 2. That means if we simplify, it becomes 3b sine theta by 2. And exactly in a similar manner, we can say yc is equal to minus. It is minus because we have chosen our y-axis we have taken our y-axis positive in the downward direction, and here yc is in the upward direction. So therefore yc is to be taken as minus, and it is minus b sine pi by 2 minus theta by 2. So it will be going to be minus b cos theta by 2. So in order to find out therefore the velocity of point C, we note we need to differentiate to get the x component of the velocity of point C and the y component of velocity of point C, because we note that during the motion both this xc and yc changes. So it means that the point C while moving will have both x component velocity and the y component velocity. That means its velocity has the component along the x direction and the component along the y direction. So therefore we need to find out what should be our velocities, and we see that these are the components and we can differentiate them and can write that this will be the case. So if we try to calculate the magnitude of the velocity, the magnitude of the velocity is of course root over vx square plus vcy square, and if you follow the simple trigonometry here, just a simple trigonometrical simplification is done to finally express the velocity of the point C in terms of the angle theta by this simple equation. So that is going to be the required magnitude of the velocity. What we have done, separately calculated the x coordinate of the point C and the y coordinate of the point C, noting both are functions of time. It indicates therefore that the point C has both x direction velocity as well as y directional velocity. So just differentiate them, find those velocities, and then take this quantity, square everything like that. And you know that you need to calculate theta dot. You need to calculate theta dot from here. So use this equation, forget this minus sign, because you know you are trying to calculate the magnitude of the whole story. So you can, you know, forget that minus sign here and can say that the velocity of point C, of course, this is giving you the magnitude of the velocity. Truly speaking, if you want to express vectorially the velocity of point C, you need to take into account this minus sign while, you know, substituting them individually in Vcx and Vcy. That means when you are substituting this theta dot and this theta dot here by this equation, you should carry this negative sign here, and that indicates that here both the components of velocities are having a negative sign. If you replace this theta dot by this equation, both these expressions will have a negative sign in front of them. What it means is that going back to this, you see the velocity of point C will have negative x component velocity. That means the velocity, one velocity component will be, say for point C, I can show this will be the x component of velocity, and our y component is also going to be negative. So the y component velocity is, you know, sorry, it will be going to be in this direction. So this will be there for the x component velocity, this will be there for the y component velocity, and the resultant of course will be the magnitude, which will be something like this. And here we need to find out the magnitude of the velocity. So therefore we can ignore that negative sign and can come that this will be the velocity. And now if you simply do the trigonometric simplification, ultimately when you replace this theta dot and then cos theta by 2, this will be pushed into the radical sign, you will find that this expression will ultimately become something like Vb by 2 into root over 8 plus sec square theta by 2. So this is just the mathematical simplification, class 10, 12 mathematical simplification you need to do. So this is an example, and we can further illustrate our this absolute motion analysis by means of a another sum. And this sum is earmarked as to be a difficult sum. So this is the last example that we will study today in this class, by which I hope that the entire absolute motion analysis method will be clear to you. So in this example, what we have, this is a mechanism. Again, we have an assembly of several rigid bodies, and this is a very important mechanism. It is written, one of the most common mechanisms is the slider crank. This mechanism is called slider crank mechanism. It is the heart of the any internal combustion engines which are normally used in petrol engine, diesel engine, in case of automobiles and cars and all, ships, big ships, etc. So it is the slider crank mechanism, and this is one of the most important mechanisms which is being studied in course of mechanical engineering. So one of the most common, and elsewhere also, apart from these common examples where this mechanism is used, apart from that, there are several other machines actually in which we use this slider crank mechanism. This is actually used for motion modification. That means wherever there is a requirement of converting the rotational motion into a reciprocating motion or vice versa, we require this sort of mechanism. So you see that one of the most common mechanisms is the slider crank. Here that is being shown, this is what is called as the crank OB. Crank will always have one point fixed. So this is crank OB. Earlier example also we have identified a crank. This is AB. This is called connecting rod, and this is the slider, or in actually the reciprocating mechanism, this is the piston. So we have, therefore, this is the slider, this is the connecting rod, and this is the crank. And we see here, we need to express the angular velocity AB of AB. We need to express the angular velocity AB and angular acceleration of the connecting rod AB in terms of the crank angle theta for the given constant crank speed omega 0. So omega 0, which is the clockwise rotation of this crank, this is taken to be constant for this problem. Take omega AB and alpha AB to be positive counterclockwise. So omega AB and alpha AB are both to be taken positive in the counterclockwise direction. Why it is so? Because you need to define this angle which is also counterclockwise. So these are therefore the positive senses of omega AB and alpha AB. So again, in this triangle, there is a triangle like that. We can apply the sine rule to find sine phi, which will be the angular orientation of this connecting rod, because we have been asked to find out the angular velocity of this connecting rod. Therefore, we need to define the orientation of this body with respect to some fixed line. So this fixed line is taken the x-axis, and the angular orientation is being defined by this angle. And we need to, just differentiate this angle to get the angular velocity and the angular acceleration. So you see, we can write this equation like this: sine phi equal to sine theta divided by L by R. L being the length of the connecting rod and R being the crank radius. We differentiate and finally simplify this to write omega AB equal to omega 0 cos theta by cos phi R by L. However, we need to express this in terms of the angle theta. So cos phi needs to be eliminated. How we can do it? Use this equation to eliminate cos phi. So you see from here, omega AB will be equal to omega 0 R by L, as it is written here. Cos theta will be written there, and from this equation, sine phi equal to sine theta by L by R. Here, from this equation, we will be able to calculate our cos phi. And how much will be cos phi? It will be like this. So substituting the cos phi expression in this equation, I get this equation. And while simplifying, the equation turns out to be omega AB equal to R by L into omega 0 cos theta by square root of 1 minus r square sine square theta by L square. And obviously, since this entire process we have plus sign, so our answer will be positive in the counterclockwise sense. So omega AB is therefore counterclockwise, truly counterclockwise in nature. Now to find out angular velocity, we need to remember that omega 0 is constant. So we don't have any differentiation of this time, of this with respect to time. In order to define the angular acceleration of the connecting rod, we need to differentiate this equation, keeping in mind this omega 0 r by L, this entire quantity is constant. So if we differentiate once again, I can say that process of differentiation will be little bit clumsy, u by v method. So u by v method differentiation is done here. I think it is not required any further explanation, just your class 12 knowledge of calculus of differentiation. Keeping in mind d theta dt, this differentiation is done with respect to time. So you need to differentiate theta, all thetas you need to differentiate. So that differentiation of theta will lead another omega 0, and one omega 0 was present earlier in this equation. Together they will constitute omega 0 square into r by L, and further algebraic simplification will ultimately bring you to this cumbersome equation. So you see this equation ultimately comes out to be as alpha AB, that means the angular acceleration of the rod, of the connecting rod AB, angular acceleration of this connecting rod AB turns out to be as alpha AB equal to omega 0 square into r by L into sine theta into r square plus L square minus 1. All these are due to trigonometric simplification, into 1 minus r square by L square sine square theta to the power 3 by 2. And here also this is shown to be positive, everything, and assuming of course this r by L square, r by L whole square minus 1 is going to be positive, because the other quantity is of course positive here. So we don't have to say anything on that. So you see that assuming the numerator is positive, we see that angular acceleration also turns out to be positive in nature. In reality, what happens, this ratio L by R, that means the length of the connecting rod to the length of the crank, which is also known as the crank radius, this ratio is termed as the obliquity ratio of the connecting rod. This is termed as the obliquity ratio of the connecting rod. Sometimes it is used, or it's reciprocal, that means r by L. That means this r by L that we have used. This is also you can take as the inverse of the obliquity ratio. In general, for the engines that we come across, this is always greater than 1. That means this r by L, this ratio is always going to be less than 1. So it means that actually the numerator, which we have written it in forcefully in the positive manner, actually this numerator is negative. So that means what it means is that in case of the reciprocating engines, normally reciprocating engines that we will come across, although the angular velocity is this way, but the angular acceleration will be in its opposite sense. So if omega AB is in this order, alpha AB will be in the clockwise sense. It is because of the, and it also looks from the geometry here. Here also it is pretty clear that the length L is greater than R. Actually, and it is actually the case that L by R is normally greater than 1. That means R by L is less than 1, and that's the way, and therefore we find that our angular acceleration of the connecting rod is really going to be negative, although it has been forcefully shown to be here positive, because we have been instructed to report the positive answer that way. So students, therefore I hope that with this introduction to our rigid body kinematics, we introduce to you the different motion geometries that we have, and we first analyze the geometry of the plane motion of a rigid body in terms of pure translation. In either it can be a rectilinear translation or it can be a curvilinear translation, and then also we explain to you the different methods. We listed the different methods, and we take one such method, that is the absolute motion analysis method, to analyze the velocity and acceleration of a rigid body or a system of rigid bodies, which is known as the mechanism. And it is very clear from the above three examples that the absolute motion analysis is really a little bit difficult one, because the underlying difficulty is to actually analyze the given geometry, and in some cases simple mechanisms also leads to complicated geometrical equations. So therefore, barring few examples, you see the absolute motion analysis is really not economically advantageous for us. So we need to consider the alternative methods, more efficient alternative methods to analyze for such cases, and particularly if your mechanism becomes complicated, your geometry essentially becomes complicated, and your equations will become elaborate and more clumsy. More elaborate algebraic simplification manipulation needs to be done, keeping in mind, of course, without forgetting the load of differentiation. So all these things keeping in mind will actually motivate us to explore the different methods, and we will continue to do that in our subsequent classes, when we will be going to take up our the study of kinematics with the other methods. Till then, when we will meet to discuss that, it's bye from my end, and thank you for watching the video.